Intro music there, people. So hi, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Author Series. And I have a very lively Chelsea Harris with us today. Hey, Chelsea.
Hey, Frank.
How are you?
I am doing wonderfully. How are you?
I am doing super well on this coming up on Equinox. We have Equinox coming up.
Yeah.
Doing quite well. Looking forward to that. And I believe you are in Michigan, yeah?
Yep. Yeah, right in the heart of Michigan, Lansing.
And is are the trees starting to spit out their little leaves and the flowers come up?
Not quite yet. The trees, everyone kind of does their own thing. So like, for instance, my tulips are starting to come up. My little baby ones are like blooming, but the older ones will probably take another month before they bloom. So as a gardener, it's a very exciting time for me but it's also really stressful. Our last frost isn't until May. And
Right.
So what I found is that like some of my really pretty flowers will come up and then there'll be a snow and they die back and some of them never revive really. And then I don't have as good of a looking garden. So I have like a very like elaborate Home Alone type like scheme for this year where like I'll rush out with like paper cups and like cover everyone if it snows. So we'll see how that goes.
That is a very awesome picture off to your left. Is that yours or whose family is that?
Mine. So this is the first painting I ever did. And my parents, like when I was 20 something, had it like mounted up on like a board. And then they were like, we're moving, take this. So now I have it, but it's my inspiration, my roots. You know, when I become a big famous painter, I don't want to forget where I started.
There you go. And if I'm not mistaken, because we had a little conversation beforehand, I think you have a really awesome picture it's off screen right now, but it's
I don't know how well
that's a little bit more modern take. There you go.
Yeah, that little guy. I doubt that you'll be able to see it very well. It's kind of hard to move, but it's a like nebular spectrum of the Supernova 1991T, which is kind of like a pet favorite of mine. I don't know do you have like a favorite supernova that you?
Yeah.
Yeah, I think it's kind of common, right? Like we have to memorize so many and somehow like you have like a favorite one. But this is part of an outreach program that I did through the Abrams Planetarium. So you can actually find this online, but it's for adults.
So what's the medium there?
That's just acrylic. So I'm very impatient. So I really like to paint with acrylic. And also I mess up very easily. So I can't do watercolor because you can't fix your mistakes with watercolor. But I did it where you're supposed to, the prompt was to paint your feelings about quarantine. This was back last year. And so it's actually called Self-Isolation.
I think we have a new classification for Supernovae here.
Yeah. Just make things more complicated for everyone.
Indeed. So on that note, dare I ask what you like to do for research, Chelsea?
Supernovae. So I really like anything like supernovae. I really love type 1A supernovae. So I actually got into physics because I wanted to study like the expansion of the universe. And then when I learned that type 1A supernovae are like one of the main ways that we do that, I just thought it was so cool, like, because it's so hard to imagine the size of the universe. And I love that type 1A supernovae are like these little beacons that are like, this is how far away I am, you know, and gives you this handle on something that is so like unfathomable. So I love that about type 1A supernovae. And so pursuing that, I got really interested in binary stars and just, you know, we have won a Nobel Prize with type 1A supernovae, but we still don't know what they are, it's just mind blowing.
Yeah. So if you ask me, I'll answer your question now. If I have a favorite one, yes, it will be the next galactic SN1A.
So it's like a future one is your favorite that hasn't been born yet.
That's right. Yeah. And hopefully by then we come up with a better classification scheme, so it doesn't come with these days 9 letters after the SN 2022 ZBT
Yeah.
AD. It's like, oh boy, we need a better scheme.
Yeah, it's like really crazy. And also like some of these supernovae. So one of my favorite recent supernovae is PTF11KX.
Mhm.
So like I talk a lot about that. I research it a lot. And what's wild is it was never even given like an SN name. Like it just is PTF11KX. Like it doesn't have that more official name. And we keep meaning to ask for one.
Yeah, yeah.
And we just keep forgetting. So it just but yeah, so now my interest is like pretty focused on like trying to suss out the binary star evolution that leads to type 1a supernovae, and how do we do that with the circumstellar medium, and trying to understand these recent events where you actually see a type 1a supernova collide with a hydrogen rich CSM, which is something people had looked for a really long time.
Right.
There's kind of this unlucky sort of circumstance type thing surrounding that whole class, whatever. It's really complicated, so I won't go into it, but in detail. But yeah, and then with supernova 2014C, which is a core collapse supernova, type 1b, that got me interested in looking more at core collapse supernovae because it just has this incredible data set of what I call delayed interaction. So this is CSM, where you have a really clean environment near the supernova, so that it looks totally normal for like 100 days. Right. And then, yeah. And then like, and then after 100 days, you just see it crash into the CSM.
Yep.
So I love those types of objects. They really challenge our the existing like theoretical models that we had, both for the binary star evolution, massive star evolution, and even what I specifically work on is the tools that we use to say like, well, what did that CSM actually look like? What was its density structure, so that you can say where it came from. So
very nice. And that is going to bring us into this very lovely APJ article, Outside the Wall, Hydrodynamics of Type 1 Supernovae Interacting with a Partially Swept Up Circumstellar Medium. And Chelsea, take us away.
Okay. So you said that no prep was required. So I did reskim this to remind myself what I had said in it.
Right.
Yeah. You know how it goes. So this abstract, the first part kind of says what I just said, which is that when we're trying to understand supernovae, we'll constrain the circumstellar medium to do that. And we found these type 1 supernovae. So these are just supernovae without hydrogen. So you can have core collapse supernovae that are type 1, or thermonuclear supernovae that are type 1. So that's the types 1A, B, and C. And in all of these, even though they have really different, even though one's core collapse, one's thermonuclear, you can still see this circumstellar medium that's at like 10 to the 16 centimeters. And as I say here, there just aren't that many models for it. So I'm trying to kind of fill out that space. And this paper specifically focuses on this one imagined scenario for what that CSM would look like, which is that it has like a wall, and then outside of that wall is some unswept material. So the formation scenario would be that you have an outburst or maybe a change in wind properties or something, and that will sweep up any existing wind or whatever into like a thin shell, and then, but if it only partially sweeps it up, you'll still have that outlying material. So so constraining that whether that wall exists in a certain system is really important, because if it was formed through something like a shock, then it should have something like this thin wall there. But if it was from a single outburst, then it wouldn't. So that's one way that you can figure out how the CSM was created. And so in this paper, when I was doing these models, what I found is that basically the relative height of that wall compared to the ejecta that are impacting it really determines how the shock is going to evolve through that CSM, and therefore what you're going to see. And so like I have here that if you have like a higher wall compared to the ejecta, then you're going to have more degeneracy between the CSM properties and the deceleration parameter. So that's how quickly the radius, how quickly the shock slows down. You're going to have slower shocks, slower forward shocks. The reverse shock is going to be stronger and go through the ejecta faster. Yes. You're going to have slower shocked ejecta, less ejecta mass than CSM mass in the shock and more mixing of ejecta into the CSM at those earlier times. So those were like kind of the main conclusions, and I could tell you about any of those if you're interested in a specific one. I don't know if we'd have time to go through every single one of them, but then as part of discussing those results, I put that in the context of the type 1b supernova 2014C. And I kind of like reanalyzed the original model that had been put forward for that by Margutti et al. 2017.
Oh, yeah.
And,
Yes.
And let's see. Yeah. So, and then kind of talk about what that means for the radio data. And then also, I think one of the like main things that I liked about the way that I did this investigation is that at the very end, while I was kind of getting this ready for submission, I was like, well, how can you even tell if the wall is there? And I should really run some simulations with no wall in it to see like when do you need to gather data to find out that this wall exists? And so that's the end of the paper. That's kind of like the last result.
Cool.
So that's within this.
All right. Very nice. As we'll start with figure 1.
Yeah. Yeah, that'll show you like the overall density structure that I was kind of trying to describe. So maybe I should have asked you to go over to it. Sorry.
What do you want to do?
Yeah, so this is the density profile that I was talking about in words before, but so the light blue is the supernova ejecta, and that the outer profile will have a really steep decline. Yeah. And then that wall that I was talking about is just that thin pink layer. And then you'll have some material outside of it. And like, we'll assume that we don't know how that material is distributed. So it could be like that blue dashed line, the green dotted line, the orange line. So the orange line would be like a wind.
Yes.
And yeah. And then to like tie it really, like I was saying, like to this physical scenario of how the CSM would be formed, the relationship between the wall density and the density of that like outer medium is constrained in these models by this eta parameter that shows up sometimes in, notation is all over the place, but and if you read some shock papers, they'll use eta to refer to the compression ratio. So a strong shock will, compress gas by a kind of like a fixed ratio given by the like blast wave conditions of the Rankine. I've never pronounced this right. Rankine-Huguenot. How do you pronounce it?
I say Rankine-Hugonio.
Hugonio. Okay. I feel like I get a little bit of like dyslexia, and I'm just like, well, I know these letters are in there. I'll just mutter something.
Jump conditions. Just say jump conditions.
Yeah. And so yeah, I do fix that eta to be either like 4 or 7. If you had really strong cooling in the shock, which I don't think you would at these densities, because I'm considering densities that are like 10 to the minus 18 grams per centimeter cubed or something. Yeah, that's scaled, so it's like not helpful at all. But but I don't think that you have strong cooling. So I do think that you'd have 4 or 7 probably as reasonable values for eta. So that's how that wall and the outer CSM are linked. And then the wall height that I was talking about is something that is not really linked to like directly, like it's not presupposed. So that is just determined by saying, like, if the maximum velocity of the shocked ejecta is 30,000 kilometers a second, and I have a wall at, radius RC naught, then that 30,000 kilometers a second ejecta is going to reach that wall at some time, the impact time. And, the supernova ejecta is freely expanding. The density drops like T to the minus 3, like I have up there. And so that kind of sets what the density of the ejecta is at the time and location of the wall. And then, you pre-specify like what the wall density is based on whatever you want to investigate. And so those two things together are going to then set the relative density of the ejecta and the wall of CSM. And that's going to turn out to be like really important. So that's why I gave it its own variable name, which I felt so bad doing. And I tried to give this figure to readers to be like, this is all the variables. All the variables you're going to see in this paper are here. And I'm so sorry.
Awesome. No, it's great. It's a nice figure.
Thanks.
Lays it out very clearly.
Yeah, it was not made with Adobe Illustrator, so I know it's not as pretty as
Uh,
what you could make.
it's beautiful. It's beautiful.
And then let's see. Oh, a figure that I remember Peter liked, I think was figure 2, that kind of like demonstrates some of the things that I had been talking about earlier. Oh no, figure 3, sorry. Figure 2 is just showing that we explore a lot of different A naught values, but figure 3, I think, is the one I was thinking of.
Okay. There we go. And
Yeah.
boom.
Yeah, so this is kind of demonstrating some of the concepts that I was just talking about, or in the abstract that I mentioned. So along the top panels, that's a high wall. So that A naught is like almost 200. And in the bottom panel, that's a very low wall, where actually the wall is less dense than the ejecta.
Yeah.
And this A naught of 0.3, that's pretty comparable to like what you would expect from self-similar evolution. So like if you go back and look at like Chevalier 1982A, there's like this equation for what the shock, where the radius of the contact discontinuity between the media. If you look at it, it basically translates to a density ratio, and this would be it. So I think of this as kind of like the self-similar A naught, where you'd expect the self-similar equations to apply more, which is something I haven't mentioned yet, so maybe I actually should. So to analyze observations of supernovae interacting with circumstellar material, the most common thing, the most well-developed thing, are these self-similar solutions. And I believe the first time that this was discussed in the context of determining the evolution of the forward shock was Chevalier 1982A. And since then, it's been heavily developed, and you can just search that paper and then look up all the places it's been cited to find a ton of tools for using that solution. And so basically, that just gives that the evolution of the shock radius will be a power law in time with the power law index, depending on the power law profiles of the supernova ejecta and the CSM. And then you can go through that. That basically gets you like 90% of where you need to go when you're trying to translate shocks into radiation. And so there's all sorts of stuff. So anyway, that bottom panel is kind of like the thing that normally you would think about, and the top panel is like what you maybe wouldn't normally think about. Right. Okay, so in the left-hand part, I'm just showing the pressure, the thermal pressure, and the y-axis is the radius. So everything on the bottom is going to be ejecta, and everything on the top is going to be CSM. And what you see when you look at the pressure is that the shock shows up really clearly. So this like yellow-orange band, that's shocked material. So that's why I use the pressure to find the shock fronts, because like that derivative is just crazy. So you can just like find those white dashed lines really easily. So that the top one then would be the forward shock, and the bottom one would be the reverse shock. And what you can see is that in radial coordinates, like the reverse shock actually goes back, like goes back down for this like high wall, because that's how strong the reverse shock is. Even though these ejecta are moving outward, it's speeding through in mass coordinates so fast, because the ejecta are basically stopped by the CSM. And you can see like, so it has like this trumpet shape in the top panel, whereas in the bottom panel, you basically see like two power laws. So that's like two lines. So that's more typical of like self-similar. So that kind of holds up there. And then those crosses are the time that the forward shock crosses the wall. So anything beyond that is in the wind. So that happens pretty early on in the evolution. Yep. And the stopping power thing is really shown in the middle panel. So this is the gas velocity, the gas speed. So this isn't like the shock speed. So initially the ejecta are very fast and the CSM is really slow. And if you have a high wall, then you see that the ejecta can't really move the wall. Like you can't really accelerate that material. And so you're gonna see then like lower line velocities, for instance, for anything that's emitting in this region. Okay. You also do have slower shock speeds here. That's not directly reflected in the gas bulk velocity, but it's the case. And you can see by the end of it that the reverse shock is down in the really deep, slow ejecta, compared to in the bottom panel where you have a lower wall. And in that case, the ejecta has a lot of power to just tell the CSM to move. And so the CSM in that case get accelerated to very high speeds, and the reverse shock is not going to be probing as far into the ejecta, which is important because like, for instance, the composition of the ejecta is going to have some sort of a radial profile. So if you're thinking about,
Yeah, I'm good.
so if you're thinking about like looking for lines or like, well, what's the abundance of the shocked material or the composition of the shocked material, like that's going to depend on where, like how far down your shock is reaching.
Yes.
And kind of like in that same vein, I'm using this code RT1D that Paul Duffel wrote, and I'm really super excited that he wrote it, in part because this is actually like such one of my favorite stories. Like I was a young grad student and I was just starting on this type of work, and I was using just a normal 1D solver to do these interaction simulations. And Paul Duffel, who is a huge Rayleigh-Taylor instability like geek, he asked me a question, and I was like a really young grad student, so this was terrifying. Every question was terrifying, much like today actually. But he was like, well, what about the Rayleigh-Taylor instability? That should be present in these systems. And I gave some stupid answer at the time, and then afterward I talked to him about it. I was like, well, I don't even know what I would do about this. And he was like, I feel like there should be some way to model this. And so then he went off and like developed that model, and that's RT1D. And I think it's really great. And I think anyone who does this work should try it out, because it feels great to get this mixing incorporated into your interaction models. So in this plot, I'm just showing like how with the different walls, you also get different levels of mixing. And I was really surprised that the high wall actually had like more mixing at early times. So like these dashed lines show you something like having a 95% pure composition. Like where is that?
Okay.
And so you can, so anything within the dashed lines is like mixed, and anything outside of the dash anything between the dotted lines and the dashed lines is like not mixed material. But anything between the two dotted lines, you have to consider that to be a mixture of it, CSM and ejecta composition. So that's going to add metals to the CSM, and it's going to add hydrogen to the ejecta. And so, you know, in interaction shocks, oftentimes people are like, well, for instance, with lines, like where is the shock? Where's the radiating material? Oh, I know. I'll look at the composition and look at the line strengths to tell me where it is. Right. And I feel like it's really important, yeah, to like answer that question of like, okay, is that technique valid, or how accurate is that? And for me, it's like when I want to go then predict the radiation signatures of this, knowing the composition in my domain is important, especially if I want to do line calculations. Yes. So those are kind of like the main, like this plot kind of shows you like the main takeaways. And I honestly just think of it as like the high wall has a lot of stopping power over the ejecta. And the higher the ejecta density compared to the wall, the more it can shove on the CSM. And to me, that's really intuitive, but it's not usually talked about. So
very nice. I can see why your co-author likes it.
Yeah. And I also tried to use like consistent like color palettes throughout the paper, which was really hard to do. So there's no viridis in this one because I had to use it for like a bunch of other plots. Yeah, I don't know really, I don't remember kind of what else is in there. I don't know if there's anything that you immediately find interesting where we should like skip to that figure and talk about that, or just kind of like go through them. Or
I'll let you drive. We can go through and talk about whatever you would like. Let's see, let's slide down. You want to say anything about figure 4 or 5?
Ooh, this is kind of important. Yeah, I'll say something quick about this. So I think that like, for instance, like with the analysis of 14C, one of the important like questions was like, when do you cross the wall? And I think that that's an important question, like regardless, because you want to know like, do I think that my observations are still in the wall or not? And like, if they are, what does that mean about that like A naught parameter? Mm-hmm. So throughout the paper, I use Viridis to this like color map here to denote A naught. So anything that's really dark is a low A naught. So it's like a low wall where the ejecta are running the game. And so I show in this plot, like your evolution in that case is really close to self-similar, which is the black dashed line. Whereas if you have the higher wall, you're going to have more deviation from the self-similar solution. And this is just for the type 1b models, which I don't know if I've said yet that I ran both type 1b and type 1a models for this paper because I'm interested in both types of supernovae. But I stress the 1bs because 14C we actually have data for, whereas for type 1a supernovae like this, we don't have like a lot of data outside of the optical. So it makes more sense to, I think, for the theory to focus on 14C for now. But yeah, and you can see like, so I did the different densities, the different like wall densities as different marker shapes in this plot, just to prove that like really in these coordinates where you're normalizing the time to the impact time and the forward shock radius to the initial contact radius, A naught really is the thing that's controlling the shape of these curves. Like you look at two curves and as long as they have similar A naught, like you can see this really well in like those teal curves that are kind of like in the middle. Like that has like all three densities together. And just because they have the same A naught, they evolve like the same way. So that really is the governing parameter for this shock evolution. Yeah. And then I come up with some functional fit because if you have a functional fit, then you can tell, like you can predict the time of shock breakout or the time that the forward shock crosses the edge of the wall. So I like to provide functional fits when I can. So in this paper, I give that, and then the like parameters that you plug into that fit are in figure 5. So it's a little bit clunky in my opinion because, you know, you have to like read off of figure, but whatever. If you use this figure, then you can kind of say like, oh, well, I think that the shock crossed the edge of the wall at this time and the impact was at this time. So like, that means that A naught is this or whatever, or, you know, how you use it will depend on what data you have, but basically it gives you a tool to do that and to look at the evolution in the wall.
Okay. Do we have the functional form anywhere? There we go.
Yeah, I think it's at the bottom, probably right there. Yeah.
Yep. Got it.
Yeah. So it's basically a power law. And I think the reason I wrote it this way was to show, because I think V forward over V ejecta max might be one of those plots or whatever. But the point is that like, I wrote it this way to show that like, once you get to low enough A naught, you will converge to just a power law evolution. So like, that's kind of nice, I guess.
Yeah, it works. Yep.
Yeah. And then for the rest of it, I think I'm looking at the evolution once the shock has crossed that wall and now you're moving to the outer medium. And so yeah, figure 6, in each panel, I'm just like varying a parameter. So the left panel is like how steep is that density gradient? And the middle is like how much of a fall is it between the wall and the outer CSM, so that eta parameter. And then the last panel is just varying the width of the wall.
Okay.
So like if you have like really thick wall, that would be the 1.3, which I think is like dot dashed. And so that'll be different. Yeah. But again, like if you have a really strong like forward shock, like the dark purple, which represents those low walls, everything's pretty much the same, regardless of the fractional width of the shell. And then the differences get a little bit more pronounced as you get to have the higher A naught. But overall, what I was really happy about is that like ultimately the evolution of this is a power law, which is great because who doesn't love a good power law?
Power laws are wonderful.
Yeah. And like, so something that actually, a measurement that can actually tell you the forward shock radius is very long baseline interferometry. So that's one of the reasons that I focus a lot on the forward shock radius, in addition to the fact that then you can get the shock speed from the derivative of the forward shock radius. So I like to give people these equations for the forward shock radius. And yeah, so that's while it's in the wall. And then once it's out of the wall, you would use a power law. But something that's crazy. So with VLBI, one of the games that they play with those data is they say, okay, I know the forward shock radius over time. and then you measure what's called the deceleration parameter. So if R, it's kind of like an equation 3. If R goes like T to the M, then you want to measure M, because in the self-similar solution, that would tell you either if you assume the CSM density profile, it tells you about the ejected density profile. If you assume the ejected density profile, it tells you about the CSM density profile. So it's something that people really like to measure, and VLBI is so amazing, and I love it so much. It's so pretty. It's so incredible that people can do it with some of these interacting supernovae. So one of the main things that they give you is M. So then I was like, okay, how much is this model where you have this detached CSM and you maybe don't have self-similar evolution, how much does that mess up your ability to use M to then uniquely infer the ejecta and CSM properties? Because in these models, like the ejecta properties are held constant. A lot of the CSM properties are held constant as well. And all that's changing is the location, basically. And so then that's figure 7. Yeah, 7. So like in this figure, the color corresponds to the steepness of the density profile. And then the line style corresponds to the width of the shell. And literally all I did was I took, for every model, I just did a power law fit to like those curves from figure 6. Yes. And I just said, what's the power law index of that fit? And I plotted it. And if it was self-similar, then everything would line up with the arrows that you see on the left. But instead, it's all over the place. And I couldn't even find anything that was like really like a guiding principle in this. It's just kind of like this forest. And I think that the main takeaway is that it's not totally certain how to interpret the deceleration parameter. And I think that that's something that definitely needs to be kept in mind when we're trying to interpret the data on these types of events.
Definitely. There's a physical message in that forest.
Yeah. And this is another thing where I think about how Paul Duffel would approach this. And I'm sure he would get in the weeds and try to figure out exactly how to like get all of these back. But to some extent, I think I'm a little bit more empirical than that, where I'm like, to some extent, it's important that it doesn't seem like there's a great way to break this degeneracy if all you have is M.
Yeah, yes.
Yeah. But what was funny is that then later when I analyzed 14C, so I won't probably go into this, but just in the discussion, the 14C data deceleration parameter actually like somehow lied like right in a little segment where there weren't that many models. So it was kind of funny. Like I thought that this would end up being really confusing, but maybe you can like get lucky. I don't know.
Yeah, that it happens.
Yeah.
Occasionally you get lucky.
Yeah. Okay. And then this is like this kind of, the figure 8 kind of comes up again later. But this is just another prediction from the self-similar model, which is like, what's the width of your shock region? And I also kind of like this because it shows sort of the logic behind why I explore the wall widths that I explore. So like the fractional extent of the wall, like delta R over R, is like you see there like 1%, 3%, 10%, 30%.
Got it.
And the reason for that is if it was formed by a shock, those are some of the characteristic, extents that you would maybe expect. And that is sort of shown here as like the black dashed line shows you the self-similar prediction for how the width of the shock should be evolving over time. But then obviously the colors represent how it actually evolves in the simulations. And it kind of gets there, but it's also kind of wonky as it tries to settle into self-similar in the outer medium.
Right.
So this was another thing where it's kind of like,
right.
I think you can safely assume a range, like especially at late times, something around 10 to 20% or whatever, but it's definitely not one of those things where you can like be very precise in that, I think.
Yep. Good point. Fair enough. Okay.
Yeah, shock speed. That's another thing people like to know, need to know. And again, it's just the same message here as always, which is the lower walls. So that dark purple color And this is, I plotted it in the top panel, especially for the forward shock speed. It's basically follows the self-similar behavior. Again, the cross marks indicate when you've crossed the wall and you're in the outer medium. But you can see that like even before you've doubled the time since impact. So for 14C, the impact was at about 100 days. And you can see like if that was a low wall system, then even by about 170 days or something, so the dark purple, like even by 170 days, if you had a low wall, you would have settled into a self-similar evolution, and nothing would look really different. Whereas if you have a high wall, so like maybe one of the like bright green curves or something, that looks really different from self-similar evolution for a long time. And also, obviously, the forward shock is much slower in these systems because the ejecta can't push as hard. For the reverse shock here, this is literally just the time derivative of the reverse shock radius. So it's a little bit, in my opinion, it's kind of counterintuitive because you want to think about how the shock is like moving backwards through the ejecta. So you need to basically correct this into the ejecta's like local frame. And I didn't bother doing that here, but like this just kind of shows sort of a similar-ish thing, which is that you get these different behaviors depending on A naught. And then I explored the reverse shock, in my opinion, in a more intuitive way in figure 10, where this is just for the 1B models. But I'm showing here, so the solid lines are from the simulation. The X's indicate when you've crossed the wall. And then as I've written here, the dashed thick lines show you what the velocity is of the ejecta that is currently crossing over and becoming shocked. And so you can really see how if you have a low wall, the ejecta do decelerate a bit, but pretty much they're just going to do what they want to do. Whereas if you have a high wall, you like the lightest green, like you really just slam that ejecta down to stopping. Yeah.
Right.
And the crazy thing about this is that these walls are not that massive. And so something that you'll see is people looking at the line widths in like optical spectra and saying, okay, well, I have a line width that is 3,000 kilometers a second or something. Therefore, I must have a very massive CSM to have done this. And I think that what this research showed me is that that type of reasoning needs to be carefully considered, because you don't necessarily have to have a massive CSM to stop the ejecta. You just need to have CSM that is more dense and has like a lot of stopping power. And that is like kind of an accident about whether or not it's more dense. So like the same density or the same mass of wall, if it's moved inward, then the ejecta will have been more dense and it'll have a different ratio. And so I think it's a pretty complicated situation. And I don't think it's very safe to just say, I see low velocities, so I must have a ton of CSM. It's like, maybe not.
It's the contrast, not necessarily. I get why people say it, though. I understand why people would phrase it that way. But
yeah, definitely. And I mean, one thing that I feel very strongly is that this is on the theorist, because I think that I think every observer wants to interpret the data as well as they can. I think everyone wants to do that, is like get as good of a picture as they can. And if we're not producing appropriate models, if we're not producing predictions that are actually directly comparable to the observations, like how are they supposed to do that? Like,
right.
So yeah.
Fair point. Okay, and there's your V forward, and let's go to 11 and 12.
Yeah, so most of this is just, yeah, it's kind of just comparison. These are like the last 2 points. Like, so in figure 11, just talk about the shocked ejecta mass. So again, that's the ejecta versus CSM mass that's shocked is another prediction of self-similar evolution. So the rightmost panel shows how you deviate from self-similar solution or the self-similar prediction. And like in particular that kind of maybe counterintuitively, if you have a high wall, so the light green lines in the right-hand panel, you actually have more CSM mass shocked than ejecta mass shocked. And that's basically just a density thing.
Right.
Like once again.
Right.
But yeah, I actually, in my analysis of 14C, talk about the middle panel here a little bit, because I think it is, so there was an X-ray peak at like 400. So again, 14C, the impact time was at like 100 days. And then they have an X-ray in the 2017 data set, it looked like it was an X-ray peak at like 400 days. I think once they got the 6-year data set, they actually found that that wasn't really a peak. It was just kind of like a fluctuation. But regardless, from the 14-day spectra, they found this emission measure, a certain emission measure, and an implied mass of CSM that was like 1 to 1.5 solar masses. And so you can see here, like, long story short, when I reanalyzed the 14C data, I said, well, I think that actually the A naught parameter that's maybe appropriate for 14C would be like this green line, like at the top, which is an A naught of about 200 or something, or 20 or something like that. So something pretty high. As you can see, that's one of my highest wall models. And so what this would kind of suggest is that the majority of that material at 400 days, which would be T over Tmp equals 4 here. So I get about 1 to 1.5 solar masses at that time is shocked in this model. But the majority of that mass is that outer CSM. So my modeling would suggest that the shock is all the way into the outer CSM by 400 days. And so in terms of using the X-ray data set, which starts at 300 days, to constrain the properties of the wall, I don't know that there is going to be a lot of power there, which is pretty unfortunate, because X-ray data are really great for constraining CSM properties. But I do think that they can still constrain the properties of the outer CSM really well, even if they're not as relevant to the wall. And it might be difficult to get it to understand if there was a wall in that case, and if so, what were its properties.
Fair enough. Okay. Yep. Fair enough.
So that figure. And then this is the CSM mixing one.
Okay.
So yeah, this was kind of surprising. I actually should probably talk to Paul more about like how to interpret this. But basically, what I found that I was kind of surprised by, like, let's just look at the dark purple curve for now. Okay. So because that one should be like the self-similar. So that's kind of like the normal interaction situation. So in like a normal interaction where you have almost equal density material, you expect the Rayleigh-Taylor instability to be in effect because of the fact that the ejecta, which are actually higher density, are being decelerated by the CSM, which is a lower density medium, which will drive the Rayleigh-Taylor instability. So in this curve, you see that the mixing, the percentage of the CSM mass that I say is polluted by ejecta, that's going up over time, which is what you'd expect as that Rayleigh-Taylor instability grows over time.
Yes.
Yeah. And what's surprising, what was really surprising to me is that I don't know, I would have thought that like that mixing would be less significant as that wall gets higher. But what I got from the simulations was this really like not monotonic behavior. So initially, as you move to the bluer colors and eventually into green, you see that like that percentage of mixing does go down. So like the next bluest thing is like below the purple thing, and like actually significantly below. And then like it starts going up again. And like to the point where then once you're at the like light green, which represents the highest wall, you actually get like really strong mixing at early times. So it just shoots up to being almost 100% mixed. Yeah. And then it isn't until actually later on in the evolution that this kind of stops happening. And then if you were to keep following this, then the Rayleigh-Taylor instability would eventually grow again, and you would see this curve go back on an uptick. Okay. But yeah, I don't know. I thought that was really crazy behavior, and huge if true, because that would mean that like in these situations, you have a lot of mixing. And
Right.
you really need to think carefully about what your composition is of the gas that's radiating and where it is and what's its speed and all that kind of thing.
Very nice.
And yeah, I
I
think
think
the
there was
last
one more where you actually got into 2014 C a bit, reinterpretations and all. And so I think this is the last figure. Wall memory, that's always a good thing. Okay.
Yeah, so this is actually I didn't have a figure about interpreting 14C because I didn't feel super comfortable about reinterpreting 14C without any radiation transport calculations.
Okay.
So that's just text only, but I pretty much explained it. But this would be like my last main point that I made in the paper, which is, so I took two models, so a high wall model and a low wall model. Oh wait, no, okay. I took two models, a high wall model and a low wall model, and then also different wall thicknesses. So these are the same line styles as in the previous figures where like the solid line is like a 10% wall thickness. And then we have thinner walls and thicker walls. So that's what the line styles mean. And then the color means the wall height.
Yes.
And all I did was, so I had my simulations, these simulations that had a wall in them. And all I did was I said, what if you just didn't have the wall? And so I just took out the wall and just continued, in this case, a wind. I continued the wind back. And I just said, like, the only interesting thing going on is that you have this huge spike in the density, and that's all that matters. And so how does that signal compare? So in the top panel, I'm showing like the percent deviation, so the difference between these two models in the forward shock radius location. And then in the bottom, it's in the width of the shock region. And the reason that's important is that these are two parameters that you get directly from very long baseline interferometry. So these are what I would consider like hydrodynamical quantities that you actually measure directly. And then like the shaded regions or like where those lines are give you an indication of what the typical VLBI error is. And basically what I found is that like you would not be able to confidently tell these apart if you were just looking at like the evolution of the forward shock radius, because pretty much everything, the difference is like less than 5% for everything besides the very thickest shell and highest wall.
Right.
And then for the wall width or the shock region width, that you might have some better luck with because you see the shaded region is like your error bar. For a lot of the time, those lines are actually outside of the error bars for like, especially for the high wall. So you have a chance of seeing that there was a shell, but I think probably you would just be like, why is this so thick? You might even be like, oh, I measured something wrong or whatever, but it's actually just because of the effect of the wall. So I think that there is some memory of the wall, but overall, I would say that if you have these later time observations, like especially, yeah, if you look at that at like later times, the delta R over RF, like it's not that big. So this is just another thing about how I really think that you need to, that first of all, I need to run radiation transport calculations on these models to see what the effect of the wall is on the luminosity. And then also just to, you know, provide guidelines and try to make sure that you get measurements early, and that if you have late time measurements, you don't overinterpret what was happening at those inner radii of the CSM.
Okay.
And I think that's everything I did in this paper, aside from the 14C stuff, which I feel like I already kind of talked about.
Very cool. Well, thank you for walking us through that. So now you get to put on your fortune teller's hat, and you know, so where does the field go over the next, let's say, couple of years? You already gave some hints, right? So one of them was that you know, these calculations do not include the radiative transfer. So are there efforts underway to do radiative transfer within these models? Are there new observations? Well, there's always new observations, but
yeah. So
so where do you see this going over, let's say, the next 5 years?
Yeah, this is a super exciting time. So I'm seeing some theoretical interest like picking up in this kind of system, in these types of systems. We have some projects that will hopefully get funded related to it, and I think other people do too. So I think the theory work is still going. The radiation transport stuff, yes, I'm doing that now. And then in terms of the observations, I am so excited. So LSST, it's just going to be crazy. Like these systems, we don't actually know how rare they are, but they're fairly rare among both 1As and 1BCs. And so something like LSST that is just collecting so much data is perfect for rare phenomena. And the really great thing about interaction is I call it a leisurely science. Like it takes so long. You can really see these signals for hundreds of days. And so I know that there at least used to be some concerns with LSST and the cadence and like how well sampled will rapidly evolving light curves be.
Right.
But you know, they should be able to say that there's some blip there and then see in the optical what happens with interaction is you get like a flattening of the optical light curve. So I think that there is a really great access point into LSST. And I actually have an undergraduate student, Jack Hernandez, who they worked to basically kind of get that started, that kind of analysis that we'll want to do with LSST. So they're doing that with ZTF data and trying to kind of like figure out how are we going to run statistics once we have something like LSST, what can we do with ZTF on the observational side, just to kind of figure out where is the CSM, how many supernovae have CSM like this, what might we be missing? And then my work is more directly on interpreting those observations and trying to say like, what does that mean physically about how the CSM got there? So the next 5 years should be really exciting. Next 10 years should be even more exciting. So yeah, it's a great time to be doing this science, in my opinion.
Awesome. That is great. That is great. Chelsea, thank you again so much for sharing your lovely article with us and giving us a future outlook.
Yeah, thank you, Frank.
All right. Thank you, everyone. And we will see you on the next one. Bye-bye. Oh, and I should end with my closeout tune.